Okay, good morning, afternoon, or evening, everybody. Welcome to the Laser Altimetry Applications for a Changing World Working with ICESat-2 Land and Vegetation Height Data training webinar. Today's event is the second in a multi-part series of ICESat-2 specific data training Earth data webinars. This is your host, Jennifer Brennan. It is 2 p.m. Eastern time, so we are going to go ahead and get started here. What I'd like to do first is begin today's webinar with some logistics information. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, please enter your questions into the Q&A panel rather than the chat located on the right side of your screen. And if you don't see the Q&A panel, what you can do is click on the three dots at the bottom of your screen, and that should pull up your panel options, and then you can insert a check mark next to the Q&A panel. Today's webinar is being recorded. The recording will be posted to our NASA Earthdata YouTube channel within a week of completion. Once completed, I will send an email to all registrants and participants that includes links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's event will be 1 hour and 15 minutes long, with an estimated 45 to 50 minutes allocated to the presentation and live demonstration, and a 15-minute question and answer period to begin after the presentation. Depending on the volume of questions that are received, we may extend the Q&A session, but we will have a hard cutoff at 3:15 p.m. Eastern Time. During today's webinar, let me actually advance the slide here. We will have 4 speakers. Our first speaker is Dr. Amy Neely. Amy is the ICESat-2 Mission Applications Lead here at NASA Goddard Space Flight Center. She will provide you with some information regarding the ICESat-2 data training webinar series. After that, we will transition to our second speaker for today, Dr. Soren Popescu. Soren is a principal investigator for NASA's ICESat-2 mission and is located at Texas A&M University. Dr. Popescu will provide an overview of the ICESat-2 mission and will also provide a comprehensive introduction to the vegetation and land height data product that is the focus for this afternoon's webinar. Our third speaker today is Dr. Tyler Sutterly. Tyler is a research scientist at the Applied Physics Laboratory, or APL, Polar Science Center at the University of Washington. Tyler will provide an introduction to SlideRule Earth, a web service that provides on-demand science data processing for ICESat-2 and other geospatial data in the cloud. He'll discuss various applications and use case examples using SlideRule. Last but certainly not least, our final speaker today is Joseph Paul, or J.P. Swinsky, a computer engineer also located at NASA Goddard Space Flight Center. He will conduct a live demonstration of an ICESat-2 data workflow using SlideRule Earth. After JP is finished with this demonstration, what we'll do then is we're going to transition to an optional final set of polling questions and then jump straight into the Q&A session. And just really quickly, before I toss it over to Amy, I wanted to cover one final note about the Q&A session. We will try to answer all of the questions within the time allotted, but if we're not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. So with that, it is my pleasure to introduce today's first speaker, Dr. Amy Neely. And Amy, with that, I'm going to stop sharing my screen and hand it over to you. All right,
Excellent.
Amy.
Thank you. All right. So welcome, everybody. I'm glad everybody could take the opportunity to be here. And my job here is to give you a brief overview of the purpose of these webinars, which we are calling a multi-part series. So today's is actually a second part in a multi-part training series. The first one was a general overview of ICESat-2 and the tool Open Altimetry to download and look at ICESat-2 data. And we will hope to have more this year. Today, obviously, we have the vegetation webinar, and I'll show you in a second. We have at least 1 or 2 more planned for the remaining year. So the purpose of these webinars is to highlight the capabilities of ICESat-2 and its data products, to build capacity, so focus on these processing tools and workflows for novel science and applications, and to bring together the community. We want more people to be able to use and understand ICESat-2 data and all that it can do. So typically in these webinars, we plan to have some sort of data product overview. Today is the vegetation data products, some sort of live demonstration of a tool that you can use to visualize those data. And lastly, we tried to include some sort of application use case or how you would actually use this data product in the real world. So as I mentioned before, we have some other webinars planned. Now, ICESat-2 is much more diverse than ICE. We can do vegetation, we can do bathymetry, hydrology, sea ice melt ponds. So there's a lot of capabilities here that we're really trying to spread the word on. So today is the vegetation. We hope to hold a bathymetry webinar on April 9th when the new bathymetry product is hopefully released before then. We will also hope to have something on sea ice and melt ponds and something on hydrology. And we will announce these webinars approximately 2 weeks ahead of time. And lastly, I just want to give a shameless plug for a bathymetry workshop that I am hosting with the US Hydro meeting. It's on March 17th of this year. Feel free to reach out to me if you have any questions or interest in this event. So once again, I just want to say thank you, and thank you to the speakers for taking time from their day to present to us their research. And I will let Soren take it away now. Please take it away, Soren, after I stop sharing. There we go. Done.
Well, thank you. Allow me to start my presentation and start sharing. So, okay. Okay, I'm hoping you can see my slide, introductory slide. So thank you, Neely, Jennifer, everybody involved with this NASA Earthdata webinar. I'm much honored to talk to you today about ICESat-2 and mostly about the ATL08, which is the land and vegetation height product. So I have one slide introducing my broader field of research. So I used the word cloud and I dumped in it the titles of my publication, and it came out that most of them are related to LiDAR, remote sensing, environment, and you can see even ICESat-2 there. So pretty broad interest working with lasers from terrestrial platforms, airborne, and for the past decade or so, my focus has been on spaceborne LiDAR, specifically ICESat-2. So ICESat-2 was launched in September 2018. It's a spaceborne photon-counting LiDAR, and the science objectives were to measure melting ice sheets and investigate how this affects sea level rise, measure and investigate changes in the mass of ice sheets and glaciers, estimate and study sea ice thickness, and the objective of interest I would estimate all of us here is the measuring of height of vegetation in forests and other ecosystems worldwide. To date, ICESat-2 has collected about 2 trillion laser shots. So that's 2 million millions, if you want to understand the significant number of shots that have been fired so far. And chances are that it has the energy to stay and fire more shots for about another decade. So it has been and will still continue to be one of the most important missions to date for assessing terrain and vegetation heights globally. I imagine most of you here are related to vegetation science, but why should you care about canopy height? So Forests are the major terrestrial carbon storage and sink ecosystems, and canopy height is one of the strong predictors of vegetation, biomass, carbon, which links vegetated ecosystems to the carbon cycles globally. And the forest canopy is the functional interface between 90% of Earth terrestrial biomass and the atmosphere. And also, if you care about forest canopies, probably you would care about fuzzy worm creatures, since an estimated 50% of terrestrial biodiversity has found home actually in forest canopies. And lastly, ATL08 has consistently been one of the most downloaded ICESat-2 data products. So lots of reasons to use ICESat-2 to study vegetation and its properties. The way ICESat-2 collects data, it's pretty important to understand this part, since it's different than other traditional imaging spaceborne sensors. It's by using 3 pairs of beams that are spaced about 3 kilometers apart. And in every pair, there's a strong beam and a weak beam that are separated about, their tracks about 90 meters. And imagine them covering the globe with ascending and descending orbits. So to the background of this slide shows you actually the planned tracks for covering the Earth. So along track, there's a laser footprint, there's a laser shot that is spaced every 70 centimeters. So you have a very dense along track coverage of footprints, and every footprint can return maybe 2 to 3 photons. So we have, along track, a profile of vegetation that is acquired by those photons. The width or the diameter of every footprint is about 13-14 meters. So they collect photons from anywhere within this 14-meter footprint, and they are geolocated to the center of the footprint. So to the right, you can see a profile through photon-counting data that is actually the ATL03 product, so just geolocated photons. And even with the naked eye, you can spot the trend in the terrestrial surface, and on top of it, you can see the canopy. And of course, there's some noise points above and below all of this. When I saw the first data output and this kind of graph, it reminded me of previous work of one of the scientists associated with ICESat and ICESat-2, in fact, Ross Nelson, who used canopy profile areas back in 1984 with a profiling airborne LiDAR to study canopy. So we are now doing pretty much the same, but from space and with a much denser coverage, and also with a much better geolocated data set. Those photons have very good geolocation properties. For those of you familiar with airborne LiDAR, to the bottom of these slides, you can see a slice that's approximately a 14-meter wide of airborne LiDAR, and on top of it, you see the photons coming from ATL03 product. So those photons clearly portray the profile of the vegetation, as you can see from both airborne and spaceborne LiDAR. NASA makes available through its NSIDC Data Center a suite of products with various levels of processing. Level 2 is the geolocated photons in ATL03. So that's what you can see towards the top left of this slide. And then a series of dedicated products for land ice height, sea ice freeboard, sea ice elevation, and so forth. The one of interest for today's presentations being the land water vegetation elevation ATL08. So ATL08 consists, as you can see also on this slide to the left, consists in those photons that now carry a photon class. So they are classified in ground photons, top of canopy photons, those dark green photons, and in between top surface, top canopy photons and ground, we have the canopy photons. So that's the photon classification in the ATL08 product. And in addition to just photon classes, this product actually reports photon metrics in 100-meter fixed segments. So we get to see a distribution of photons with various statistics per 100-meter segments, which is something that's very useful for relating photons and vegetation, three-dimensional structure to other biophysical parameters. An upcoming product is the gridded elevation canopy height, ATL18, and pretty soon I will talk to you about a somewhat similar canopy height model that my lab group has derived, and I wanted to make sure that you understand this is not the ATL18 product, which will have a different spatial resolution, but it covers the ATL18 will cover the Earth globally, whereas the product that I'll be talking to you is only at continental extent. ATL08, the land and vegetation height product, is now at version 6, and it contains a long track heights above the WGS84 ellipsoid for ground and canopy surfaces. And as I mentioned earlier, those photons are processed in fixed 100-meter segments, and the data is available from NSIDC for download. There are multiple software tools available to you as well to play with the data, and the files are available in the HDF5 format. The data is provided in granules, which span about 1/14 of an actual orbit, and you will get to see a map of ATL08 region and granule boundaries similar to what I display here to the right. So with various regions, and they're separated in ascending and descending orbits with different region numbers, and that's what will help you identify, locate, and download relevant ATL08 data. I'll spend a few minutes here talking about the photon classification. So imagine getting ATL03 data, those unclassified photons, and running them through a series of filters to remove noise and to identify those patterns in the photons that correspond to terrain, canopy, and top of canopy. So all of those steps, I won't go through every one of them in detail, but you can find a description of those in the ATL08 ATBD document. And this photon classification is actually implemented through an algorithm that is called DRAGON. It stands for Differential, Regressive, and Gaussian Adaptive Nearest Neighbor, developed by Amy Neuenschwander at the University of Texas. So after running ATL03 through all these filters to find ground, to refine ground finding and top of canopy as well, we end up with labeled photons in ground canopy and top of canopy, and then those photons are summarized in terms of statistical properties in 100-meter segments. There are multiple photon classification algorithms out there. In fact, one that was very appropriately named, yet another photon classifier, YAPSI, is also known. My lab has looked at about 2 algorithms, one of them including a moving window to process those photons, and another one involving random forest reclassification. Once we have, the ATL08 product with classified photons, we can actually refine those classes through some machine learning approaches, which is something pursued by one of my PhD students, Mei Lu, here at Texas A&M University. To summarize the photon classification, the top part of this slide shows you the raw ICESat-2 ATL03 photons, and down at the bottom, the same data set, but this time with classified photons with the top of canopy, and ground. And to the right, you can see actually the track segment that overlays vegetation and even some clear-cut areas. So if you would like to look for tools to process ATL08, definitely visit the NSIDC website. But we developed a few of them here at Texas A&M as well. And one of them is the photon labeler. The idea was to be able to create even your own label data sets for using machine learning to classify photons, or in the lack of maybe some other validation data sets like airborne LiDAR to assess where ground top of canopy would be to validate some other data products. So let's delve a bit more into the ATL08 product. So those photons with the classes, top of canopy, ground, and the canopy photons are again summarized in 100-meter fixed segments. And there's a fairly large list of variables associated with those photons. Some of them that are most commonly used in other studies to derive canopy structure are those metrics, absolute and relative height metrics, with the common percentiles from 5 all the way up to 95th percent. So they have been proven in a few studies to be well correlated to biophysical properties of canopy. If you wonder how good the photons, whether ATL03 or ATL08, portray canopy heights and terrain, we have done a validation study where we looked at ICESat-2 data over multiple ecozones within the continental United States and looked at ground elevations and canopy properties by comparing ATL08 photons to airborne LiDAR data sets. So we actually sliced those 14-meter long, narrow airborne LiDAR data sets from open topography or the NEON, NSF NEON database, and we compared that or those properties to the ATL08 product, and we were very pleased to see that those photons actually portray very well terrain elevation. Here's a summary of our validation efforts. The bias for terrain height between ATL08 and airborne LiDAR is 18 centimeters with a mean absolute error of 1.2 meters. So really very strong correlation there between photons and airborne LiDAR for characterizing terrain elevation. With respect to canopy properties, we investigated both the strong and the weak beams and looked at the time of acquisition, whether day or night acquisition, and we looked at multiple ecozones within the continental United States that were spanning from desert and xeric shrublands to Mediterranean forest, woodlands, scrub, to temperate broadleaf mixed forests and conifer forests. So those graphs to the right show you, the relationship between, for example, percent bias for height metrics for strong and weak beam. And the height metrics I refer to here are those percentiles that I mentioned earlier that are present in the ATL08 product. For various ecozones or various ecosystem types, of course, you'd expect that relationship to vary. And indeed, for some of the grasslands, savanna, and shrublands, the relationship between the two data sets proved to be weaker as compared to maybe the temperate conifer forests and broadleaf forests. The question that's also maybe on most of your mind is, how do we go from those profiles of canopy properties to actually generating some meaningful map products of biophysical parameters such as canopy height, canopy cover, and even biomass? So the idea is to fill in between those tracks with ancillary data sets that could consist in imagery products like Landsat or Sentinel-2 or any other image product that you find meaningful, but also a list of many other ancillary data sets, at least in the US, such as those that are produced by Landfire, which also compute canopy cover, canopy height in multiple products. So they could be used actually as ancillary data sets to model between our tracks, ICESat-2 tracks, and photon properties in whatever segment length you want, and those products to generate a wall-to-wall mapping product. So in this case, I'm showing you the flowchart for generating the continental scale canopy height map, where we used, as I mentioned earlier, a list of ancillary variables with machine learning methods, in this case XGBoost. So it's an improved version of random forest to generate those canopy height maps for all ecozones within the continental US. We validated the product two ways. One is with model validation. We split the data into training and testing with an 85 to 15% split, but also we used independent airborne LiDAR from Open Topography and NEON to assess independently the canopy height maps. So all of this is presented in a recent manuscript that came out last year, a publication now for mapping vegetation canopy height within the continental United States. Maybe some of you following this flowchart may wonder, how do we get from tracks of ATL08 to relating those ICESat-2 heights to other variables like Landsat imagery, for example? So we used a sampling strategy along every track of available data from 2019 to 2021, the majority of the data being from 2020. And to access such a large data set for the continental US, we use SlideRule. So I'm putting in a plug for the next two speakers, for Tyler and JP, who will talk to you more about ATL08 and SlideRule. So we collected a large number of samples of canopy height that cover all the ecozones, meaningful ecozones within the continental US, and related those in 20-meter segments, so not 100-meter segments in ATL08, but we chose to work with 20-meter segments and relate the height properties to the ancillary data sets for filling in between the blanks. So with respect to model performance, with the holdout data, we had a very good, I would say, relationship. The R-square was 0.76 for the entire continental US. Of course, this relationship varied between different vegetation types, as you can see pretty soon. So when looking at variable importance, out of all these data sets that we used, we tried to use Landsat data gap fill product within the growing season to avoid the influence of snow-covered areas that would bias our models. But we used some other variables like elevation, ecoregion, slope, biome type. So the meaningful part to look at here is that pie chart that shows you the contribution of various variables to the whole model here. We see Landsat variables about 18%, topography 18%, and then those bioecological variables 33%, and landfire already available canopy height products were significant at about 33%. That's with respect to variable importance. If you would like to find greater details, I would recommend looking into the publication in Remote Sensing of Environment. We validated the canopy height model for the continental US and looked at different biome types by using airborne LiDAR datasets derived from or downloaded from Open Topography and the NEON dataset. So this is the independent validation with Open Topography ALS. Overall, for the entire canopy height map at continental scale, we got an R-square of 0.72, which we thought was very good with a bias of minus 1.7 meters. We also looked at other canopy height products, and we were curious to see how our map compared to a map derived using JEDI data. So there's a publication by Potapov from 2020 where they generated a global extent. So that's one is at global scale, canopy height map at 30 meters as well. And we wanted to see how our map compares to existing products. So we found a favorable comparison here towards ICESat-2 with both Open Topography ALS selected randomly within our biomes and the NEON canopy height model maps available through the NEON data set. I'd like to draw your attention to some of the comparisons here for different biomes. So we were very happy to see at least that the major ecozones within a continental US, like the temperate broadleaf forest, the conifer forest, had a very good comparison with R-squares up to 0.63. You can see the two products, the JEDI and the ICESat-2 derived maps here. And we saw a similar trend with both maps. The lowest correlation here was observed for temperate grasslands, savannas, and shrublands. But of course, you probably would expect that such sparse vegetation with low canopy height would not correlate well with those spaceborne data sets. There's a difference in over the whole continental US between those two maps, and we explore it here, but I won't have time to go into a whole lot of details. I want to show you some other data products briefly. So this is the canopy height map that you can download from our lab website. It's available now in tiles that correspond to the Landsat analysis ready data tiles. But also, I'm hoping soon they will be available through NSIDC in cloud optimized GeoTIFF files. Other studies that you could pursue with ICESat-2 and ATL08 would be to map canopy cover, for example. And here's a publication that proposes multiple formulas to use those photons, a number of photons in canopy, top of canopy or ground, to estimate canopy cover. It has the data with those formulas have been used to compute a gridded map at countries scale for Turkey. There was a visiting scientist here at the lab that produced this with ICESat-2 data. Here's a study that looked at biomass burning emissions with ICESat-2 by looking at biomass maps before and after fires to estimate what was emitted during those fires, for example, in California. There are other efforts from other scientists for mapping biomass. I'll just mention 3 of them here. With Amy Neuschwander's study recently published in RSC last year, looking at the boreal biomass density, same boreal biomass in Scandinavia with the Varvia et al., and an earlier study that looked at simulated data, but with both JEDI, ICESat-2, and NISAR for mapping biomass in California. We also have our own efforts for mapping biomass. This is a prototype. Before we thought we would apply it at continental scale, and we obtained some really encouraging R-square values. There's a manuscript in review right now about 0.77 for mapping biomass in the Pacific Northwest when compared to FIA forest inventory and analysis data. A look ahead, and I'm getting close to finishing my presentation here, is to maybe generate similar biomass maps at continental scale or canopy cover or global canopy height maps. And since we accumulated data for over 5 years, I'm sure that you will see more studies looking at change detection over the 5 years of the mission. With that, I appreciate your attention, and I know questions will be addressed at the end of the webinar, but thank you for your attention, and now I will pass it on to Tyler.
Hi, everybody. I am Tyler, and I am here to present a tool along with my colleague JP. I'm at the University of Washington, and JP is at NASA Goddard Space Flight Center, and we are developers and colleagues for a team called SlideRule. SlideRule started under ICESat-2 and has been ongoing and developing over the past 5 years. ICESat-2 is a laser altimeter. It's lasers in space. And as Soren said, it sort of collects data in these profiles. You can think of them as a long track point clouds that are repeated over these 70-centimeter bursts, where each of the footprints, as Soren said, is about 11 meters in diameter. It collects data over 6 beams that are collected into these 3 beam pairs. Each of the beam pairs is separated by 90 meters. This setup was created to both collect as much data as possible to have the 3 beam pairs separated by 3 kilometers each, but also to be able to instantaneously collect along across track slopes so that you could measure very steep surfaces, but also measuring a breadth of areas by having the pairs. ICESat-2, as Soren said, was created to help quantify how our ice sheets and glaciers are changing and their contributions to sea level rise and how that connects to climate. And also quantifying how the regional signatures of these ice sheets are changing, whether it's snowfall or dynamics, and figuring out why. The other main thing of what ICESat-2 was designed to do was to measure sea ice thickness and how the interaction between ice, ocean, and atmosphere in terms of our energy budget and our mass budget is affecting our globe. And then the third, which is the letter that is a lowercase, is land, is to measure vegetation. And so measuring how canopies of and vegetation structure globally. And ICESat-2 has been up for over 6 years. It was launched in October of 2018. And in that time, we have developed a number of different products, as Soren showed sort of a product map. This is the same thing, but very simplified. So starting with the data that is downlink from the satellite, that's our level 0. That gets repackaged a little bit and some other variables are added in the level 1. And then level 2 is the big one. That's that long track geolocated photon height product. That is latitude, longitude, time, and height for every single photon that is close to the surface that ICESat-2 collects. This is trillions of photons. And so it's gotten to be a very big product. But since we've been up for over 6 years, we're starting to think about new ways that this photon data can be used. The ones that the product have put out, we do averaging over these segments to create really good measurements of, say, vegetation or surfaces of sea ice, land ice, lakes, oceans. And then those along track science products are aggregated again to create gridded products, such as ATL18 that should be coming out next year. We also make gridded products for land ice, for sea ice, and for hydrology and oceans. SlideRule is starting to think of, well, we're getting all this data, and there are new ways that we can start to think about how this data should be used. Scientists that created these products are brilliant, but we can think about everyone being a scientist and generate a product that you want to fit your need. SlideRule is a cloud-based science data service that provides a simple and fast way to get data and process it the way you want, and to get products that fit your applications best. We came in with a few different objectives. One is to make it publicly accessible and open access, so you can look at all the code that we've ever made for this product. It's on our GitHub, and so you can see exactly what it is. There's nothing behind the curtain. We try to do exactly what we say. We also try to make it super simple so that you can do what you want without being an absolute expert in how ICESat-2 works. We have on-demand scaling, so we can do really big jobs and really small jobs timely and fast without incurring a lot of costs when no one is using our service. We also don't want you to have to worry about what file types are or things like that. We just want you to be able to get data quickly and easily so that you can make plots and do your analysis as simple as possible. Make it as customizable and generalized as possible so that you can make little tweaks, such as how long you want your segments to be or how you want your photons to be classified, so that you can do the science that just fits your application best. And then we work all the time, so we are trying to minimize our downtime, staying up as possible, but also to deploy new algorithms, improvements, bug fixes, respond to issues, be intermediaries between yourselves to get stuff done and the engineers. So we are here for you. SlideRule works as being sort of an in-between between you on the left through a Jupyter notebook or a new web client and the data on the right. We do all of our computing on AWS, Amazon Web Services, and we are doing our computing in the same region as where NSIDC, the National Snow and Ice Data Center, stores data for NASA. So this is an AWS US West 2. We do fast queries, fast subsetting, and data processing so that you can get this data in seconds to minutes instead of trying to download all this data into an archive and doing processing on your side. The first algorithm we ever put together is ATL06, which is the land ice height algorithm, but don't let the name fool you. It's really good at measuring surfaces. So here we take photons, chunk them into a segment, and then gradually lock onto where that surface is to create a tight window of photons around the surface. They're sloping surfaces, so it'll work with areas that aren't just flat. And we have been able to add in additional photon classifiers so that you can select only ground photons or only canopy photons based on, or there's these new sort of photon algorithms that Soren mentioned, like YAPC, so that you can tailor how you select your photons in order to get the best fit for your science application. This works very, very well at capturing the effects of small-scale surface topography, and enabling the different photon classification schemes mean that you can get ground photons in the presence of heavily canopy for forests. The second set of algorithms we put together is ATL08, which is land and vegetation structure. This is a collaboration between the SlideRule teams and our colleagues at the University of Texas at Austin. taking those photon classifications from Dragon to be able to get vegetation statistics at any segment length you want. So if you want to be at a different length than the 100 meters that is standard in ATL08, we provide a quick and easy tool for you to do that. And so you can create custom vegetation structure. And we also allow quick and easy subsetting of the geolocated photon data, so you can actually see what this photon data looks like behind the hood. A very exciting thing that we are working on really hard and is going to be released soon is topobathymetry. ICESat-2 is green, 532 nanometers, which means that it actually penetrates through clear seawater and lake water in order to measure what the ocean floor and sea floor looks like to tens of meters of depth. So we're going to be generating the gold standard product. It's being processed right now, which will be released to NSIDC in the coming months. And we're also going to unlock the API so that you can generate custom products just like we do with the other algorithms. So you can generate bathymetry for regions of interest coming soon, which is very, very exciting. Use cases that people use SlideRule for, one of the first big ones was using for terrestrial snow cover. Here, this was a graduate student at the University of Washington, and she used SlideRule to look at ground returns, and then being able, because these are steep areas of mountain snow, she used very short segment lengths and used Dragon photons in order to lock onto the ground, in order to look at how snow depth has changed. So she compared ICESat-2 with the snow off LiDAR survey, and was able to look at a few seasons of data and then compared it with what are called snowtail sites, so on the ground snow measurements, and being able to see this looks like a really good comparison in time. So we can tell not just at these snowtail sites, but anywhere where you have a good snow off LiDAR survey or good snow off DEM, how much snow it has occurred. So you can measure terrestrial snow cover from space using ICESat-2. One of the really big and exciting works that people have used SlideRule for is to look at icebergs. So icebergs sort of fall in between the cracks of the standard data product. It wasn't something that was really devised. It's not quite sea ice. It's not quite land ice. It's over the sea, but it's taller than regular sea ice. And a team at ESR, Lori Padman and Susan Howard, worked really hard to be able to map every single iceberg that ICESat-2 has seen in the Southern Ocean by using very short segment length and tailoring how the YAPC, this photon classification, worked in order to best lock into icebergs. So we can see how the standard land ice algorithm looked at trying to determine icebergs at the top, and how with looking at shorter segment length that were tailored towards icebergs, you can really see the entire shape of these bergs. And so this is a project that we're working on releasing soon. And it's, again, one of the biggest things that we've done, and it's awesome that they were able to do this work. One of the things that I'm a part of is looking at glacier crevasses, so really sharp and steep areas. This is an area that the standard ICESat-2 product really was envisioning. We know that crevasses have been a problem for laser altimeters since we started flying over glaciers in the early 90s with LiDARs. And so one way that we could use SlideRule here is that we used different photon classification, and we use really short segment lengths so we can get not an aliased sampling of these surfaces, but a really locked on measurement of the surface. On the right, this is at Bird Glacier, but we've done this for a number of glaciers in Greenland and also on floating ice shelves in Antarctica. So a little summary of SlideRule: we're really cost effective. We can scale up, we can scale down. We are a service that exists, and we're trying to exist for the long term. We're really responsive. We're seconds to minutes, not even time to get your coffee. You can just click go and get results soon, as JP will show with our new web client. We're trying to work on really well-documented APIs. We have documentation on our website, trying to limit our downtime and enable new functionality all the time. So please get in contact with us if you want to add something new. We're adding new data sets all the time. So we're not just ICESat-2, we have JEDI, we're adding more raster sampling and more. But another great thing is this is all open access. You can look at and see how this works under the hood and do this work for yourself. You don't need to be at NASA Goddard Space Flight Center in order to get data done the way that you want to. You can use our work and use our algorithms to get this done for your science application. So thanks for listening. We have a website, a GitHub, documentation. Again, you can always contact us. We always love responding to people that want to use our tools. We also have private clusters available. So if you want to do something really, really big, we can set up a private cluster so that no one is interfering with your job. You can just go and get stuff done fast. And we're also starting to enable custom algorithms, including Docker containers, to be able to do custom work. And with that, I'm going to hand it over to JP, who's going to do a live demo using our brand new web client. So thank you for listening.
Thanks, Tyler. Let me share my screen. Actually, before I show the new web client, I actually want to just quickly show what it has looked like for the past couple of years. So the main way of using SlideRule has been through Python, typically either through a script or a Jupyter notebook. And so this is the API, where you would import SlideRule in your notebook, initialize it. You set some parameters yourself in a dictionary, and then you'd make a call to one of the APIs. And then we would return a data frame back that would look like this. So that's how it's been. That's going to continue to be supported. But I'm really excited to share with you guys a preview of our new web client. It'll be officially released about mid-March. We're getting the last tweaks and kinks out, but I'm excited to give you guys a preview of that right now. Just make sure.
I currently don't see any content. Okay.
Yeah, sorry,
It's okay. No
sharing is just
problem.
taking me a second here.
It's all right. No problem.
There we go. Okay, you guys see that?
Yes, perfect. Thank you.
Great, thank you. So this is a application that runs fully in your browser and makes REST-like API calls to the servers running in US West 2. So if you have a region of interest that you're interested in, and I was playing around with it this morning, and I saw some fun stuff in Yellowstone. So I'll put a request right here. And you hit run, and it will make that request to SlideRule, and it pulled, let's see, there's pulled 10,000 different ATL06 points. So actually it calculated them. So what just happened right there is a request. Remember, I showed you that JSON request string that had to be constructed in your notebook. Well, it built that request behind the scenes, and it made that request to the servers. And 50, 70 different ATL03 granules were in parallel pulled and subsetted, and then they were run through the ATL06 surface fitting algorithm that was re-implemented for SlideRule. And so then it pops up all the different tracks. And so you can kind of see on the left what the different tracks are, and you can see on the right a scatter plot of the surfaces. So, if you wanted to do different surface, that's a different surface there. So then if you want to see the photons that go along with it, so I just hit that button. It made another request to the server, and it now just pulled the ATL03 photons that are corresponding, that were used to generate the ATL06 products. So you kind of zoom in. Let me see. I'll get it. Make it a little bit bigger. So you can see here, this is using the ATL03 confidence level to classify the photons, and then the red is where the surface fitting algorithm fit the surface. And you can see how that's performing. It's locking onto the high confidence photons. But you can also look at the ATL08 classification. So we also, when we make that request to get all of the ATL03 photons, we also make a request to the ATL08 product as well, and we combine them together, and we give you the ATL08 classifications. And so then you can see what that looks like. It's when we fit photons to the when we fit the surface to the photon cloud, it's often the case when there's dense vegetation that the surface is biased upward because it's seeing the vegetation as surface. So if that happens, and it's hard, it's kind of hard to find a use case. I saved one that was good in another window, but when that happens, what you can do is you can go back and you have the advanced tab and you can do a photon selection. And now you can say, I only want to fit photons to the ground photons that ATL08 has classified, or you could do Canopy or Topobathymetry, things like that. And then when you do that, you can rerun the request, and it will, instead of just fitting the photons to all of the photons, it'll fit it just to the ground photons, and it'll return back a different fit. I think we're pretty close. There's cases where it's really great to see, like you'll see the bias, and then you'll see when you refit it to the ground, it comes back down. But really, we're just trying to give you all of the tools necessary. So here's, this is not bad. Yeah, so I'll make this a little bit bigger so everyone can see it more easily. So you can, perfect. So you can see right here, like there's some dense vegetation here. If you used all the photons, it would actually bias this surface fit upward a little bit. But because we're locking on only to the ground classified photons that ATL08 provides, it gives a much better answer. So this algorithm that was, again, initially designed for ice sheets can be adapted really well for vegetated areas when using ATL08 classifications. And then all the data is yours. So you can export it to your local computer. It's actually already sitting in your local computer right now. That's why it's really quick to export it to a Parquet. You can go back over all your requests. So you can see I've made maybe 25, 26 requests here. You can add descriptions for it. So if you wanted to keep track of them, you can clear them or delete them. You have all the parameters of the request, things like that. And then on the main request page, if you zoom out, you can also view the different areas that you've worked. Like you can see what I was doing earlier this morning, just looking at different areas to see if I can find a good one that would show some good vegetation. So with that, I think we're at time, and I'll stop sharing and hand it back over to Jennifer.
Okay, great. Thank you so much, JP. At this point, I'm going to open up the final polling questions and then jump straight into the, because we're running a little bit behind, and jump straight into the Q&A here. All right, so we do have a question from the chat. I'll cover that first. The first question is, have you considered expanding your product to Alaska?
I believe that question is for me. So yes, definitely. We were even considering going to, global scale, but it's just a matter of having enough manpower for now. So Alaska, definitely. I don't have a time frame for it, but I'm hoping that it would come reasonably soon.
Okay, well, thank you so much, Soren. So now I'm going to hop down to the Q&A for our next question. My apologies, excuse me. All right. Have to just, if you could bear with me. Okay, so the next question is a little bit longer, and the question is, I am curious if the method proposed in COB 2023 for ground elevation using the progressive modified filter on the ATL08 photons has been compared to the other methods discussed by Dr. Popescu. And then there is an additional reference. Let me go up here. COB AR, domain R, Sucre, RS, et al. 2023, which is improved terrain estimation from spaceborne LiDAR in tropical peatlands using spatial filtering. Is that sufficient information to respond? I'm happy to repeat if necessary. And it might be that we need to take a look at this and address it offline if that reference is not coming, immediately coming to mind. Anybody have a response to the question? If not, I'll move on to the next one, and then we'll hopefully be able to address this question either with a typed response in the Q&A, or certainly our speakers can follow up with the participant offline. Okay. Seems like we might need a little bit to look into it a little bit and take a look at that specific reference. And so the next question is, okay, so it was insightful to see the use of the random forest and XGBoost. How is the current status of deep learning algorithms in this area? Do random forest and XGBoost provide specific benefits over other algorithms?
Well, I could venture to give a quick response to that, but anybody else, Tyler or JP, are welcome to step in. So random forest has the advantage of being a largely studied and applied algorithm, provides very good results, and it's fast. Okay, XGBoost with its boosted trees and improvement in the way it builds those trees, it's slightly slower, but provides very good results as well. So these two have been used quite extensively in other work as well. I cited some other studies in my presentation. I think what a current student did make way, and there is a table in one of my last slides. She investigated multiple models to see their performance, and to our surprise, maybe, because there are other fancier algorithms, there are stacked algorithms and so forth. Random forest provided the best results. So it's hard to tell sometimes. I guess someone would just have to try multiple algorithms and see, depending on the distribution of the data sets, the number of variables, possible correlation between those variables, and so forth. And that's how someone would decide on which model it's best for a particular application. But there was something that came quickly to my mind. If there's anything else to add, please do so.
Okay, thank you so much, Sora. The next question is, and I just want to remind everybody, if you have a question and you have posed it in the chat, it would be very, very helpful if you could also add that to the Q&A log. Okay, so the next question is actually from the chat. How many more years will the ICESat-2 mission and data capture continue? Hasn't it lasted longer than initial expectations?
I'll answer that one. ICESat-2 is currently predicted to last until the mid-2030s. Current timelines are 2034, I believe. That's going to be dependent on solar cycle and laser health, but right now everything's looking very healthy for us to last about another decade. ICESat-2 is beyond its original mission lifetime, as many satellites do reach that. The end of prime mission I believe was in 2021, end of 2021. And so we're beyond that. We're in our extended mission phase, but everything is looking very healthy for us to last much, much longer and collect a whole lot more data.
Well, that really sounds fantastic, Tyler. Thanks so much for that response. And our next question is, I noticed that there are differing numbers mentioned in relation to the footprint of the laser on the ground. 14 meters and 11 meters were both mentioned. Also, the documentation for the ATL products seems to vary depending on which year the information is presented. Is there a definitive consensus as to the appropriate ground footprint captured per shot, or does that vary by year? Again, happy to repeat the 3 parts if needed. Just let me know.
I got it again. So this is work that Lori Magruder has been doing out of the University of Texas. So various places on Earth, we put in these corner cube retroreflectors. It's like these little mirrors that are about the size of your pinky fingernail, and they return the laser energy very strongly. And so we can set up these little arrays to try to measure the footprint size on Earth. And it has evolved as we've gotten more data and more returns for these corner cube retroreflectors. So early on, we thought it was going to be closer to about 17 meters, but we've over the years been able to get it closer to about 11 meters on our estimates. So early estimates were bigger footprints, later estimates, and I think the most definitive right now is a little under 11 meters.
Okay, well, thank you again, Tyler. The next question is also coming from the chat. How accurate can we expect from the, okay, what is the expected accuracy from the snow depth measurement?
ICESat-2 has centimeter level precision, typically over flat surfaces. So the accuracy of a snow depth measurement here is going to be how accurate ICESat-2 is, how sloped your surface is. So it's a function of off-pointing angle of the satellite. So if you're not on that center beam, but if you're on one of the more off-pointed beams, slope of the surface, and also how good your DEM is. So if you have a really bad snow off DEM, you're not going to have a really good snow measurement. So you need really good measurements between all of them. So it's going to be a little bit dependent on your region of interest and your DEM, but overall, I think that it's definitely possible to get good snow depth measurements, but it's going to be regionally dependent.
Okay, well, thank you again. The next question is actually for Soren. The question is, I see in the Akturk et al. 2023 paper, you use ICESat-2 data on Google Earth Engine platform. Can you comment about the ease of using GEE for working with ICESat-2 data?
So currently, ICESat-2 data is not available on GEE, mostly because GEE is very good at handling rasterized data set, and less so at handling data with the structure that ICESat-2 has. But I'm hoping that some of the products, including the Canopy height map, will be made available in GEE as well. So I already started some discussions with the GEE engineers to figure this out. But first, I think, would be to have the data available through NSIDC. So the way we completed the study, GE is really good at organizing all your variables that could be used as independent variables to predict some parameter of interest, whether it's canopy cover or height. So once you are able to bring in your heights, your ICESat-2 either heights or some other parameters in GEE, you can run models to output a map that is a wall-to-wall product. So we have gone through a simplistic exercise like that with students taking my class even this semester. They are actually online right now. So we use though a model map to in GEE, like the Potapov et al. That's very easy to access. But if you want to model your own product, you'd have to bring in those heights in GEE or use GEE to very efficiently organize your own data sets. And then use sort of a hybrid approach, bring them down from the cloud down to your machine, to your desktop, and run your models locally. So these are two ways: working in the cloud, fully bring your data up there, or at least organize your variables and download them to run your models.
Okay, thank you, Soren. So it might be that this next question I was about to read off here has already been answered. So Titus, if your question was not answered, if you could let me know in the chat, that would be really helpful. So I'm going to bear with me while we've got about 4 minutes left in this Q&A session. So bear with me as I pull up the next question. Okay. Okay, yes, there's quite a few responses. Okay, so the question is, are ICESat and JEDI missions complementary missions? Why or when should I use one over another? I assume this question is, really geared toward the topic, the land and vegetation height topic for today's webinar. If anybody would like to take a stab at a response here. There we go. Perfect.
I can take a quick stab, but of course, Tyler or JP could pitch in. There are different type of laser altimeters from space. JEDI is a full waveform type sensor. ICESat-2 is a photon counting sensor. The footprint size is different, but also the coverage is different. So JEDI is not able to sample the northern latitudes. So in that sense, you may say that they are complementary missions. Okay, ICESat-2 provides coverage above the JEDI limit. So in that sense, again, they would be complementary. But I think another better, data use for both would be to compensate for the sampling pattern in both, and actually use both. And there are, from what I know, there are current efforts to actually use both data sets to compensate for the sampling pattern and densify your sampling of whether heights of other parameters that could help you with biomass or canopy cover to create a product that's a wall-to-wall map. So you have to be mindful of the fact that JEDI had a gap in data collection. ICESat-2 has provided continuous coverage, but putting the two data sets together would densify the sampling and likely improve our wall-to-wall products.
Well, thank you so much. And I think this next question will probably be our last question for this afternoon's webinar event. Do you have guides or recommendations for converting ICESat-2 data to geotiffs?
That's a great question. So it depends on the product. Some of the products are already rasters. So geotiff is a raster format. And so those ones, I believe, and I think NSIDC folks could chime in, they're using their surfaces, you might be able to export it to geotiff directly if it's not already in that format. Point clouds to rasters is a little bit more complicated and depends on a number of different things. We, on the Landau side, do produce raster products from the ATL11 data, which is a point cloud data. I would say I don't really have a recommendation. I would first start with the data that's already in a raster if it works for your application. Soren mentioned a few times that ATL18 is coming, but that's not until next year, unfortunately. So it's a little bit complicated, I think. But if it's already a raster, I believe NSIDC has services to convert that.
Okay, well, thank you so much, Tyler. And given that we are at the limits for our webinar this afternoon, thank you so much to all of our participants for your excellent questions today. Thank you to our 4 speakers, JP Swinsky, Soren Popescu, Tyler Sutterly, and also Amy Neely. We really appreciate your subject matter expertise and your contributions today. Thanks to my backup hosts, Geraldine and Joseph. And yeah, so I think we hope to see you at an upcoming webinar. What I will do at this point is leave the virtual meeting space opened, and for another 10 minutes or so, if you think of a question you'd like for us to forward along to our panelists from the NSIDC DAAC or our speakers, please feel free to enter that into the Q&A or even in the chat, and I will be sending that information along to our speakers today. So thanks so much, everybody. At this point, we'll log off from the audio components, but I'll leave the virtual meeting space open for an additional 10 minutes. All right, everyone. Thanks so much. Take care now. All right, goodbye, everybody.
Bye, thanks.